Okay, so good afternoon, ladies and gentlemen. A very warm welcome to the BAA Spring Meeting webinar. It does seem somewhat incredible that 7 weeks ago I was in a place called Cottingham near Hull, introducing back to basics, and the world seems to have changed considerably since then. I was looking forward to that stage too. There was a deep sky meeting coming up. There was the practical astronomy show, the BAA March meeting, Winchester, the Nottingham one here, Mercury and Venus meeting, George Alcott lecture, and the Elgin summer meeting, all going to go ahead, but now no longer. So what I would like to say though, it's been particularly pleasing as far as the BAA is concerned that we've been able to continue astronomy within the lockdown period. And what I'd like to do is to thank Dominic for giving up his time this afternoon to host this webinar. But I would really like to do a personal thanks to Andy Wilson, who I think has possibly nipped back out into the garden, having helped set up the meeting today, for his technology skills in setting this up and getting us basically online and being able to provide the weekly webinars every Wednesday evening. And also for enabling us to enable the staff at Bredington House, because the RAS has closed Bredington House, and so the staff are now able to work remotely, mainly due to Andy's efforts. So a very big thank you to him. So as far as today is concerned, none of us have had to travel up to Nottingham. The one-day meeting initially was on cosmology, galaxies, and exoplanets. And our speaker today, Professor Simon Goodwin, is a professor of theoretical astrophysics at the University of Sheffield. And he was due to talk as part of the original meeting on star and planet formation, in line with the cosmology and galaxies and the exoplanets. But what we decided to do for the webinar is, rather than to take up your whole day, was to concentrate on the exoplanets section. So Simon has very kindly agreed to amend his talk slightly. So he's now going to be talking, is there anybody out there? And we're also then going to have Roger Dimmock, the exoplanet director for the BAA, talking, as well as the role of the section and what we're doing as far as amateurs. So as far as Simon's talk is concerned, we've discovered over 4,000 exoplanets. This obviously begs the question, does life exist on any of those planets? And this afternoon, Simon will talk about how we found the exoplanets initially, and looking at the next timeline over the next 5 years as to whether the technology is going to be available to search for life on those planets. Assuming it is, then will we find anything, and what might life be? Will it be intelligent life? Some people say we haven't got intelligent life in some areas of the world at the moment. But so without further ado, if I may ask Simon if he'd like to share his screen with his presentation, and then we'll go on for this afternoon. So thanks so much indeed.
Right, thanks very much. So can you all see this?
Yes, it's appearing on the screen.
Oh, fantastic. Yeah, so hope you're all keeping safe and well. This is all slightly unusual, but I've never given a talk from my kitchen before. But what I want to talk about is something that's really interested me since I was about 10, which is sort of planets, aliens, spaceships, and dinosaurs, and the question really of, is there alien life out there, what it might be like, and do we have any chance of finding it? And the amazing thing is, as I'll explain, we are 5-ish years away from the technology potentially to discover alien life. Now, whether we do or not, we don't know, but we're very, very close to the technology that's going to enable us to do this. So the last 25 years or so, since about 1995, have seen an explosion of a whole new area of astrophysics, which is exoplanets. So the first extrasolar planet was discovered in 1995 by Mayer and Coelho, and the discovery rate of these has gone through the roof. So every time I give this talk, I have to look up the number. The best website really for this is something called exoplanet.eu, the Extrasolar Planets Encyclopedia, which is a brilliant database of everything we've found so far. So about an hour ago, I went and looked it up, and we're currently sat on about 4,255 confirmed planets. That's confirmed planets, suspected planets, there's thousands more. It's just taking the people who work on this sort of thing a while to analyze the data and just confirm that they really are planets and then publish the next paper with usually nowadays hundreds of new planets included. So we know that planets are really common. These are all around stars, generally speaking, similar to the sun, that are relatively nearby to us in our local sort of environment within the Milky Way. And planets are really common. There are many, many, many more times planets than there are stars in the galaxy, we think. So this means our galaxy contains hundreds of billions of planets. So even though we've only discovered 4,255 so far, this is telling us these things are really, really common. The reason it took us up until about 1995 to discover planets is that looking for planets around other stars is really difficult. Our essential problem with planets is, compared to stars, they are very, very, very faint. A day like this is perfect for it. So I don't know what it's like where you are, but it's really lovely and sunny here. And stars, like the sun, are producing huge amounts of energy through nuclear fusion. And this means that if you look at a distant star, generally speaking, it's going to be many millions, if not billions of times brighter than any planets around it. So there are a few dozen planets that we've actually directly seen. So this is an example of one of the early ones where we have actually seen planets. So this is a rather boringly named system called HR 8799. And oops. Earlier we could see my pointer. We can't anymore. Oh well, I will talk my way through it. So the blob in the middle is where people have tried to remove the light from the star. They've done a pretty good job of this, but there's still a big smear at the middle of this where there's just the star gets in the way. But in this particular system, there's three things labeled B, C, and D, which are, we think, planetary mass objects, probably a few times bigger than Jupiter. Trouble is that the region that the starlight has blobbed out, in the bottom right-hand corner, there's a scale bar there. It's 0.5 arc seconds, so that's the angular size. But underneath it, it's got 20 AU. So the size of that bar, and so the size of this blob is about 20 AU. So these are astronomical units. The Earth-Sun distance is 1 astronomical unit. So the Earth will be hidden right in the middle of this blob. And even Neptune's out at about 30 AU. So our entire solar system will be hidden inside these blobs. So this seems to be a slightly unusual system with 3 large, very Jupiter mass planets, very, very long way away from the star, way, way beyond sort of 30, 40 AU. So these are big planets. We can see them directly. We can get information about them. But anything interesting, especially if you're interested in life, that's going to live a lot closer. These are much further away than Pluto. So any moons that these have got are going to be frozen solid. So these are really, really cold. So if you're interested in life, these are not places you want to look. So because stars are so bright, the way we find virtually all planets is by what are called indirect methods. So you don't actually see the planet. What you do is you look at the nice bright star that you can see very easily, and you look for something it does that tells you it's got planets. So the 2 most successful ways of finding planets so far have been, the very first way we looked for things is due to the Doppler shift. The Doppler shift in sound is something we're all familiar with. If you stand by the side of the road and a car goes past relatively fast, you hear this sort of sound. And that's the pitch of the sound from it changing. As it's coming towards you, the sound waves it's giving out, it's actually traveling at a fair fraction of the speed of sound. So it squashes them together and reduces their wavelength. And so you get a slightly different pitch. As it's moving away from you, it stretches them out, increases the wavelength of the sound. And our ears are sensitive enough to pick this up, and cars travel a reasonable fraction of the speed of sound. The thing is, that car is also doing the same thing to the light. As it's coming towards you, the light waves it's giving out, it's catching up on them, it's squeezing them together a little bit, and the light coming from the car is slightly bluer, a blue shift. As it's moving away from you, it stretches out. The wavelength makes it slightly redder, which is a redshift. Most people who know something about astronomy have heard of redshift, because if we look at other galaxies, we see that all of them have a redshift. So they all appear to be moving away from us, which suggests the universe is expanding, which is the idea that leads us to sort of, that there was a big bang, that the universe is expanding now, so it was smaller in the past. The thing with galaxies is they move at hundreds of kilometers a second. So the sort of shift they do for the light is really easily observable. You could observe that really easily in the sort of 1910s. What we do when we're looking for planets is we look at the star, and what we're looking for is a periodic change in the redshift and the blue shift. If we think of our solar system, we normally think of the sun sat in the middle and all the planets going around it. That's almost true, but not quite. For most intents and purposes, that's fine, but actually what happens is all the planets and the sun orbit what's called the center of mass. So that's where, if you took a stick and put two weights on either end, it's where you put your finger to balance it. Both weights are equal, then you put your finger in the middle. In the solar system, most of the mass is in the sun, 99% of it. Well, 99.9% of it, in fact. But there is mass in other things, most of it in Jupiter, but the center of mass of the solar system isn't at the center of the sun. It's, generally speaking, it wobbles around a bit as the planets move, but it's round about where the surface of the sun is. So from outside, if you were to observe the sun, you would see it orbiting this center of mass. Not very fast. It's typically speaking sort of meters per second, but meter per second movement does give you a blue shift and a red shift. And it's for the past about 25 years or so, we've had instruments sensitive enough to actually pick that up. And putting that in an everyday context, a meter a second is about a walking pace. So we've now got instruments sensitive enough to see the shift in light that would be caused by you just walking along. If you were walking away from it, it would be able to pick up your redshift. So the idea is you look at lots of stars, and if there are no planets, the star just sits there. You don't see any periodic change in the motion of the star. If it's got planets, you see this periodic change. So due to the Earth, you'd see the sun go around in a year. Due to Jupiter, you'd see the sun move around at the center of mass in 11 years. And so we just look at stars and try and find this shift in their motions that tells us there's a planet there. Great thing about this is it tells you how far away the planet is, and it tells you how heavy the planet is as well. So this is a really good way of getting information on how massive planets are. There is a seemingly much simpler way of doing it, which we've only really been doing in sort of getting a lot of planets out of for the past 10 or so years, which, oops, I did not want to do that. Hitting the wrong buttons. Which is something called transits. So most of you have probably heard of the Kepler satellite that NASA put up, and this was a transit hunt. So this is what seems like a really easy idea, that if, as we're looking at an extrasolar planetary system, the planet moves in front of the face of the star, then it blocks out a bit of the starlight. And so as it passes across, so in this figure, as it goes from 1 to 2 to 3, if you look at the brightness of the brightness of the star drops. And how much it drops tells you what the radius of the planet is, how sort of large the planet is compared to the star. And so you look at a star and you look for something like this happening. Trouble is that one of these transits will only happen for a few hours every year, or every one of the planet's years. So if you've got a planet in a 3-day orbit, one of these will happen every 3 days. If you've got a planet in an orbit like the Earth's, one of these will happen every year. And it happens for a few hours. So you've got to be looking at it when that happens. There's also all sorts of other things that can cause effects like this. One of the most common is just things in our solar system. So if you've got an asteroid in our solar system that happens to pass across the face of the star, you would see a very similar effect. So you never believe it if you just see one. You need at least 3 of these before you start believing that you've got a planet going around that star. So you've got to be looking at the star for a few hours when this happens. So you've got to be quite lucky there. And also, it's got to be inclined such that this actually happens. So even if a star has got planets, in only about 1% of cases will we ever see a transit. Most of the time, this planet, as we look at it, never passes across the face of the star. So what you need to do is monitor, ideally constantly, as many stars as possible. And that was the real breakthrough with Kepler. It was put up to just look at millions of stars constantly. And so it's got a huge amount of data that they're still getting their way through. It's sort of broken at the moment. It's still doing its job a little bit, but it's not as good as it was before. Basically, one of its gyroscopes went, so it can't point as well as it used to be able to. About a year ago, a new satellite went up called TESS, the Terrestrial Exoplanet Searcher, which is looking at nearby bright stars and trying to monitor as many of those as possible and looking for things the size of the Earth passing across the planet, the face of the star. So there's lots and lots of effort now going into finding planets by transits. There's a few other methods which are nowhere near as successful, so I won't bother talking about those. But it's largely a mixture of transits and Doppler method, which has given us the 4,000 and odd planets that we've found so far. So if we use the Doppler method, that gives us the mass of the planet. If we've got the transit method, it gives us the radius of the planet. Ideally, we'd like to use both of them at the same time, and then we get a mass and a radius, so we get a density of the planet, so we've got an idea of what it's made of. So this is a rather busy plot. So this, on the y-axis, is the mass of the planet in Earth masses. So Jupiter's about 300 Earth masses, against the distance away from the star in astronomical units. So the Earth-Sun distance is 1, Jupiter's at about 5, Neptune's at about 30. So the green circles on here are Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. And all the other dots and triangles and all the other symbols there are, this is about a year old, but these are all planets that we've discovered. And so there's a lot of planets with large masses, between 100 and up to about 10,000 times the mass of the Earth. These are really big things like Jupiter, or even more massive than Jupiter, so big gas giants. There's also quite a lot of stuff that's appeared over the past 10 years ago. So towards the bottom of this diagram, there's a huge red smear at the bottom, which are things largely found by Kepler, which are round about a little bit bigger than the mass of the Earth, or round about the mass of the Earth. So what we're finding is there's lots and lots and lots of planets out there. Some of them seem to be things like things in our solar system. So we're finding a lot of things, because they're pretty easy to find, that are like Jupiter and Saturn, big gas giant planets. Although what's weird, you'll notice here, is our Jupiter and Saturn are quite far out in our solar system. A lot of other solar systems have big gassy planets really close to the star. In fact, the very first extrasolar planet that was found was one of these, something in a Jupiter mass object in about a 3-day orbit. So these things are called hot Jupiters, and this has completely revolutionized the way we think about sort of planet formation and even our own solar system. That it's given us a lot of clues when we look at these different solar systems. Our solar system is not typical. Every solar system you look at seems to be different and weird. It's often called the planetary zoo. That you look out there and there's no such thing as a standard solar system. Now, if you're interested in looking for life, then big gas giant planets, all these things towards the top, about the size of Jupiter and Saturn, probably not where you want to look. Now, some of them might have moons which have life on, but we can't see their moons, so it's a bit of a moot point at the moment. Where we're really interested in looking is down towards the bottom, where the green circle with an E in is where Earth is. And there's one thing we know about life and where life can exist is it can exist on a planet about the size and mass of the Earth and about the distance the Earth is away from a star like the Sun. So this is where we're really sort of concentrating, sort of looking for life elsewhere, is to look at these planets we're finding whose masses are round about the Earth's, whose distance is fairly far away from the stars, often what's called the habitable zone, where you'd expect temperatures to be about right for liquid water. So looking at about where the Earth and Venus lie on here and targeting planets there as potential places to look for life. So if we look at our solar system, it's the one example we've got where we actually know a lot about things. Then in the inner solar system, we've got the Earth, which obviously has life. And then we've also got Mars and Venus. We've got Mercury as well, but ignore Mercury. It's a boring ball of rock and it's far too close to the sun. Now, an interesting thing when we look at our solar system is that the Earth and Venus, from what we know about extrasolar planetary systems, where we just, if we're lucky, we know both the mass and the radius, the Earth and Venus are basically identical. They have the same mass. Venus is slightly smaller, but the same mass and the same radius. And they're made of the same stuff. They have iron cores and rocky mantles and a rocky crust. And so from a distance, and with all the information we have at the moment, we wouldn't be able to tell the difference between the Earth and the Venus. If we look at Mars, it's a bit small, but actually Mars, as somewhere that might have life, is a much better bet than Venus. Because just knowing about the masses and radii of these things and the distances from the star wouldn't tell you very much. What we know when we look very closely at these, because we share a solar system with them, is that Venus is a hellhole. Venus's atmosphere is about 100 times thicker than the Earth's. It's almost purely carbon dioxide. And that gives it an incredible greenhouse effect. And so it's got surface temperatures which are hot enough to melt lead. Mars is much, much nicer. Okay, it's a bit cold, but we know it has water underneath its surface. Liquid water used to flow in the past. So from the point of view of the solar system, the Earth clearly has life. Mars might have done in the past, might do today. Venus could have done in the past, almost certainly doesn't today. But really the key thing is at the moment, we wouldn't be able to tell the difference between an Earth and a Venus. They, as far as we would know, would look exactly the same. So there's a little bit of a warning. I do a course on this for our undergraduates, and I always bang on about this, that when you see in the media any sort of claims about we've found a potentially habitable planet, don't believe them. We have no idea. Because the temperature of a planet depends on two things we do know, which is how bright, how luminous the star is that it's going around and how far away it is. So that essentially tells you how much energy hits the planet. But there's two things we have no idea about, which are really, really important. One is the reflectivity. It's often called the albedo of the planet. So how much of that light that the energy that hits the planet gets reflected back into space. Venus actually reflects most of it. That's why Venus is so bright. It's covered in cloud. It reflects about 70% of the sunlight that falls on it. Mars actually is really good at maintaining the sunlight. It reflects only about 15%. The Earth reflects about 33%. About a third of the light that hits, the energy that hits the Earth gets reflected straight back into space. So how much it reflects back into space matters. And we have no idea what that value is. And also, by far the most important thing probably is what is the atmosphere, how thick is it, and what is it made of? Because that sets the greenhouse effect, how much energy the planet can keep and how much it can keep the temperature up. In the case of Venus, its greenhouse effect, because incredibly thick carbon dioxide atmosphere, is about 400 degrees. And that makes it a really, really unpleasant place. Mars has got an incredibly thin atmosphere, so its greenhouse effect is essentially nothing. It's about 4 degrees. The Earth, actually, it matters. It's about 40 degrees. So we're worrying about changing the atmosphere, putting more carbon dioxide in the atmosphere, potentially increasing the temperature by a few degrees, but our atmosphere gives us a 40-degree greenhouse effect anyway. So it's a small change on the greenhouse effect we already have. So without knowing details in particular of the planet's atmosphere, we have no idea of what the temperature's like, whether this planet is habitable or not. So when you see in the media people going, oh yes, this planet could have a habitable surface temperature, well, it could, or it could not. And right now we have no idea. But this is the exciting bit, in a few years we will. The search for extrasolar planets, categorizing extrasolar planets, is one of the big science drivers behind building the next generation of telescopes. So currently the biggest telescopes are about 10 meters in diameter. So that's pretty hefty. But we're pushing to a next generation of telescopes, of which are by far the best, and I'm not just saying that because the UK is involved in this, but it's definitely the best, is the one being built by ESO, the European Southern Observatory, which is the European Extremely Large Telescope. So this is being built in Chile, very close to, currently, some of the best telescopes in the world. They're not quite the biggest, but they are some of the best, is the VLT, the Very Large Telescope. And they're about 8 meters in diameter. We're pushing, and this is currently being built, to build the Extremely Large Telescope, which is going to be 40 meters in diameter. And there's plans on the drawing board for OWL, the Overwhelmingly Large Telescope, which is designed to be about 100 meters. Not sure we'll see that in my lifetime, but so we've gone from very to extreme to overwhelmingly large, at which point I think we've run out of superlatives. It's about €1 billion that's been spent on this, but that's spread between about 17 countries. Mostly European, but Brazil joined about a year ago, which was good because they brought the last bit of the money that was needed to build it. The plan is that first light, so the first time this will actually look up at the sky and be able to take an image, will be about 2025. I have a distinct feeling the current pandemic is going to push this back, but not far, probably a couple of years or so. So within the next 5, 6, 7 years, this thing should be there. The money is in place. They're currently building it. The instrument's being built for it. It will be up and running soon. And this, the reason you want to build this, there's many, many science reasons to build this. If you talk to a cosmologist, then a bigger telescope that can collect more light, can see galaxies further away. If you're interested in exoplanets, then the wonderful thing about this is it allows you to start characterizing them. And it allows you to start taking what are called transit spectra and getting an idea of what those planets are like and potentially finding life. So that's the reason I'm so excited in this. It's really going to be game-changing. And the way it does this is by looking at what's in the atmospheres of the planets. Because we live on the Earth, we tend to think that everything about the Earth is fairly normal. But actually the Earth is really weird. For a start, the Earth has a lot of liquid water. Most of our surface is covered with liquid water. And you've got to be in a very fine range of temperatures and pressures to get that working. And also our atmosphere is weird. Our atmosphere is a mixture of nitrogen, which is about 80% of it, and oxygen, which is about 20% of it, and then a little bit of other stuff. That is a really weird atmosphere. In particular, the oxygen, because oxygen is an extremely reactive gas. The only reason you can have a lot of oxygen in our atmosphere is because things, plants largely, are continuously making it. If you killed off all plant life on the Earth, then all the oxygen would disappear in about 5,000 years. Things would burn, it would rust, it would oxidize things. Oxygen is really reactive. So the only reason we've got a lot of oxygen in our atmosphere is because plants are making it. They need to get hold of carbon. And so when we look here, we've got sort of a spectrum. So this is taking the light from the planet and then putting it through a prism and spreading it out into different colors, different wavelengths. And what you see is that in some places, light is missing. And that's because as light tries to escape from the planet, certain molecules and atoms absorb it and stop it getting out. So what you're essentially seeing here is the greenhouse effect, that light, in this case infrared light, around about 10 microns, is trying to escape from these planets. And there's a huge feature in all three of these planets, which is carbon dioxide. Carbon dioxide is really, really good at stopping light of around about 14 microns, which the Earth gives out a lot of its energy at around about that wavelength, from getting out. And it stops it escaping, traps it, and makes the planet warmer than it would be. Venus's case, 400 degrees warmer than it would otherwise be. But what spectra can do is they let you know what's in the atmospheres. Depending on what is being blocked, you can see what's in the atmosphere. So in the case of Venus and Mars, all we see that's missing is carbon dioxide. And that's telling us that their atmospheres are almost entirely carbon dioxide. There's nothing else particularly interesting in their atmospheres. And because they're our next door planets, we know this. The Earth, even if you know nothing about spectroscopy, you can see that Venus and Mars look very similar. The Earth looks really weird, looks very, very different. There's this big feature from carbon dioxide, the carbon dioxide in our atmosphere blocking the light trying to escape, but also it's down in a lot of places. An awful lot of that is due to water. Water vapor is also a very good greenhouse gas. So water vapor is blocking light leaving the Earth. From the point of view of an alien looking at the Earth from a large distance, what that would tell you is the Earth is a wet planet. It has lakes and oceans and enough of these things that it can fill the atmosphere with water vapor as well. And so what you're looking at there is a damp planet. But the particularly interesting thing in here is there's a feature marked O3, which is ozone. And that is the smoking gun that goes, the Earth has life. Ozone, and everybody's heard of ozone, but it's one of those weird things, not a lot of people know what it is. So ozone you get in the stratosphere, and ultraviolet light from the sun comes in and it hits oxygen molecules, O2, and it breaks them apart. Then you've got oxygen atoms. And oxygen atoms really, really, really want to react with something. In the stratosphere, there's nitrogen, which is essentially inert, so it can't react with those. So what your oxygen atom does is it finds an oxygen molecule, an O2, and joins with that. And then that gets broken apart by ultraviolet radiation. So this is why we're interested often in the ozone layer, is that this constant creation and destruction of ozone stops ultraviolet light getting down to the surface, just soaks it up in the stratosphere. From the point of view of looking for life on other planets, seeing this signature of ozone is telling you there's a significant amount of oxygen in the atmosphere. And the only thing we know of that can put significant amounts of oxygen in the atmosphere, certainly to make it 20%, is life. So this will be your smoking gun that would go, this is a planet where we're fairly confident that what we're seeing is a living planet. This is probably the sort of thing we need to find to sort of argue the toss for getting enough money to build a 100-meter telescope to have a really good look at this and really find out in detail whether we've discovered aliens. So, I keep hitting the wrong buttons. So that's the essential way we go and look for life. Finding a signature of oxygen is giving us a really, really strong hint that this could well be a living planet, and you would really want to target it and find out a lot more about it. Trouble is, not finding oxygen doesn't tell you it isn't a living planet. If we look back at the history of the evolution of the Earth's atmosphere, well, when the Earth was very young, we don't know really very well what the atmosphere was made of. Probably a lot of water vapor, ammonia, methane, nitrogen was in there as well. carbon dioxide. Volcanoes give out carbon dioxide. So as time went on, the carbon dioxide content of the Earth's atmosphere probably went up. But actually, there was no oxygen in our atmosphere at all until about 2 billion years ago. There was something called the Great Oxygenation Event. So the Earth's about 4.5 billion years old. So for the first 2.5 billion years, if we'd have looked at the Earth, we wouldn't have seen oxygen in the atmosphere. We'd have no idea that there was life there. Even during the Great Oxygenation Event, so 2-ish billion years ago, the oxygen levels in the Earth's atmosphere only went up to 2 or 3%. So not very much, and that would be tough to see. Maybe we could see it, but that would be very, very tough to see. In the bottom right, we've got a plot of sort of over the past billion years, the oxygen content in the Earth's atmosphere. And it was only a little over 600 million years ago that actually the oxygen content of the Earth's atmosphere went up to anything close to present day levels. Now, interestingly, one thing this figure shows you is that our current level of 20% there's nothing special about that. It's just what it happens to be now. It's fluctuated over the past few hundred million years between sort of 15% and we think 35%. About 35% in the Carboniferous, about 300 million years ago. It seems that oxygen levels were really, really, really high. One of the reasons we know this is life had moved onto the land in the form of plants about 50 million years before this. And at this point, insects had moved onto the land, but no other animals had. So the land was totally dominated by giant insects. And there were things that couldn't possibly exist in our current atmosphere. So dragonflies that were a meter long, that if they were around now, couldn't get enough oxygen. So oxygen levels vary. But for the Earth, it's only actually in the relatively recent past that there will be enough oxygen in our atmosphere for us to actually notice it. So if we don't see oxygen, it's not telling us that we're not seeing a living planet. But if we do see oxygen, we're seeing a living planet, seeing probably quite an evolved living planet, quite possibly one with some quite high-level life forms on it. So we're 5 or so years away from the ability to look for alien life. Are we going to find any? No idea. That's what makes this so interesting, is we have absolutely no idea what we're going to find. It's going to be a case of going and looking. Maybe we find lots and lots of living planets nearby. Maybe we look and everything we find looks like Venus or Mars. There's also the question of what we're looking for. If you look back through the Earth's history, then for most of the Earth's history, up until really about 550 million years ago in the Cambrian explosion, life on Earth was bacteria, single-celled organisms. First multicellular organisms appeared about 1 billion years ago, but life didn't actually get into anything complex in the way that we think of it when you look out your window and you see trees and birds and things like that, until about 550 million years ago. And even then, that was in the oceans. It didn't really start getting onto the land until about 350 million years ago. So if life is common, it might be that we just find lots of bacteria, single-celled organisms. Much more exciting will be finding something more sophisticated, plants, animals. And possibly more interesting or more worrying, depending on your point of view, will be discovering intelligent aliens and the potential of technology. And a lot of people who sort of think about astrobiology, the general consensus, and I think I agree with this general consensus, is that probably bacteria and single-celled organisms are pretty common. There's a line of argument for this that runs that the Earth is 4.5 billion years old. We have fossil evidence for life 3.8 billion years ago. So that's not long after the Earth formed. We know life was definitely present, and present in significant enough quantities that it could leave fossil evidence that we can find 3.8 billion years later. So life must have been very well established on the Earth 3.8 billion years ago. there's increasingly dodgy evidence as you go further and further back, but possibly more than 4 billion years ago. There is some evidence that maybe life, maybe we actually see the evidence of life back then. And so this suggests that life appearing so quickly on the Earth, it might mean that possibly life is easy to make, that the process of going from not living things, chemistry and physics, to making biology and single-celled organisms isn't actually that difficult a thing to do. The Earth seems to have done it very quickly. If it is quite easy to do, that would suggest that bacteria, single-celled organisms, should be pretty common. And there's tentative evidence that maybe there's life on Mars at the moment, life in the past and possibly even now. So possibly simple life is common. Now, this would be really exciting, but I think most people, when they think about aliens, don't think about bacteria. How about plants and simple animals? As I sort of mentioned, it took a long time for life on Earth to go from single-celled organisms to multicellular life even. That took most of the period of the Earth. It's only about a billion years ago that multicellular life appeared. And things like plants and animals, in the sense that we think of them, and large things, didn't appear until 550 million years ago. Well, they seem to have appeared really suddenly. This is an event called the Cambrian explosion, where fossils are boring, really interesting. In about a 10 million year period, fossils suddenly appear of really quite advanced fish and also plants and all sorts of stuff. So the question here is, okay, the Earth did this, but the Earth sort of had to, because if the Earth hadn't done this, we wouldn't be here to ask these questions. Is this jump, even if single-celled life is common, is this jump to multicellular life and complex life, is this difficult? Took a reasonably long time on the Earth. Did the Earth actually do this quite quickly? The galaxy is only about 10 billion years old. The sun's about half the age of and the Earth about half the age of the galaxy. So if this typically takes a very long time, then maybe our galaxy is full of living planets, but they've all got very, very simple life on them. And it's extremely rare that you get to the point that we did 550 million years ago of exploding into sort of advanced complex life in plants and animals. Then there's the question of how many of these aliens that we might find are intelligent and how many of them have technology. Now, I've sort of split that up because it does seem to be a different question. I've deliberately had a picture here of dolphins, because dolphins are clearly intelligent, but they don't have technology. So if we discovered a planet with life on it and it was a planet that had dolphins on it, we'd have discovered a planet with intelligent life. We would just have no way of knowing because we can't look closely enough to spot dolphins. And dolphins are absolutely obviously intelligent. There's a wonderful thing they do, especially adolescent dolphins. There's videos on YouTube and doing this. It's fantastic to watch. Pufferfish have got a defense against being eaten. So they give out a neurotoxin. So if you eat a whole pufferfish, you die. The thing is, dolphins have discovered that in small doses, it's actually hallucinogenic and basically get high on it. And so particularly adolescent dolphins will find a pufferfish, give it a quick squeeze, and then pass it around. And then it'll sit there high as kites. and if that is not a sign of intelligent life, I'm not entirely sure what is. But for us to be able to see that there was an intelligence there, it would need to be technological. There would need to be something it was doing that we could spot and go, aha, we've got radio signals or something like that that would give away a technology. For some reason, it appears that the humans are the only species who've ever taken their intelligence and turned it to technology. And we don't know why. There's various arguments people come up with for this. One of the best ones, I think, is fire. As far as we know, humans are the only species ever to have tamed fire. That fire, rather than being this random thing that appears and that you're scared of, we learned to harness it, and then we learned to produce it at will. That allowed us to cook, it allowed us to work metals. So maybe it's something like that. Can you harness fire? And that's what you need to make this jump to technology. So it could be we've got a galaxy that's full of life, and actually there's quite a lot of plants and animals. And when you've got animals, a lot of those are intelligent. But actually, the number of species that are technological are extremely rare. And there's a possible argument that suggests that actually technological intelligences are rare, and this is something called the Fermi Paradox, which is, when you look at our galaxy, so this is a picture of another galaxy, it's pretty much like our galaxy. Our galaxy is about 60,000 light years, it's 20,000 parsecs across, contains about 400 billion stars. And so you can ask the question, well, how long would it take technological intelligence to go everywhere in the galaxy? Your first thought would be, oh, that's going to take a long time. But you can come up with an idea of what's called a von Neumann probe. So this is a self-replicating spaceship. So you build a spaceship, you send it out to the nearest star, gets there, starts a mining operation, builds some factories, builds copies of itself. Those copies go out, they build copies themselves, and you get exponential growth, thing we're all very familiar with at the moment. And the thing is, with exponential growth, it gets very big very quickly. And you can work out, so back of the envelope calculation, that within about 10 million years, you would have trillions of von Neumann probes, having started with only one, and that they would have filled the entire galaxy. So the Fermi Paradox, as first sort of phrased by Enrico Fermi in the 50s, was, well, if there's intelligent aliens out there, where are they? So the fact that we have no good evidence for intelligent aliens and technological civilizations, they don't seem to have visited us, then maybe that says they're very rare, or maybe it says they're not actually that bothered in visiting us. Because, done it again. Because when we think of sort of alien technological civilizations, we tend to think of the thing on the left. Everybody who claims to have had an alien encounter, it's almost always with something that looks like this. This is the classic grey alien, basically a human, but just with big eyes. But actually, if you're going to move out into space and try and colonize space, you probably wouldn't want to do it as a biological civilization. You'd probably do it as a machine-based civilization. So I believe people have been abducted by aliens far more if they claim they've been abducted by something that looked like the thing on the right. So, and if you've got a machine-based civilization, it stops caring about planets so much. So maybe they're hanging around in our solar system, just watching us. Maybe they have no interest in us whatsoever. Or maybe they're on their way. They've just spotted we're appearing as a technological civilization. They're coming to wipe us out as an emerging threat. My personal feeling is alien technological civilizations are exceedingly rare. So, is there anybody out there? No idea. But the wonderful thing is we are a few years away from the technology to start having an idea. Maybe we will find something. If life is common, it should be around us somewhere, we should be able to find it. But we're there, we're nearly there. So, thank you. I shall stop sharing now. And I think I'll open things up for questions.
Very good. Simon, thanks so much indeed for that. Very thought-provoking. With what we'll now do is we'll have a questions. If you'd like to stop sharing your screen, that's great. Thank you very much. So what we'll now do is have a question and answer session, and on your screen you should be able to have, there's a box marked Q&A.
Oh, I can see that.
So what we've got is, what I would suggest you do is, if I read them out and then you respond to me, then it save other people having to look at the screen. So we've got excellent talk, thank you. 2 questions. On the plot with the exoplanet mass versus distance from the star, has anyone ever plotted exoplanet mass as a proportion of its star mass against distance? Any thoughts on that one, Simon?
Yes, people have plotted this in everything against everything, looking for any trends that you might be able to find. I'm not sure off the top of my head. One thing I do know is there does seem to be a link between stellar mass and planet mass. So when you look at most of the stars we've looked at so far have been stars very much like the sun, but people are now starting to probe in particular lower mass stars, what are called M dwarfs, red dwarfs. And what we find is that extrasolar planetary systems do seem to be common around these red dwarfs, but the planets are of lower mass. So there does seem to be a relationship between the mass of the star and the mass of the planets, which is sort of what we'd expect, because we think that planets form in disks that are around young stars, and we see these disks around young stars, and they are related to the mass of the star. Basically, these disks from which you can form planets are usually about 10% the mass of the star. So the lower the mass of the star, the less material you've got. You've also got a problem here that it depends on how many heavy elements are there, because you've got to build planets up. Most of the mass of a star and of the disk around the star is hydrogen and helium. And about, for the sun, about 2% of it is other stuff. And so this what's called metallicity matters. And your second question here, why are there no exoplanets on the plot where Uranus and Neptune reside? It's a good question. It's, as you go down, the two ways we find planets most of the time, sort of where, so the Doppler method and the transit method, you need to observe something for a whole orbit. And so the further away from the star you go, the longer you have to observe it before you see anything. So if we were trying to find Neptune by transits, we'd have to wait several hundred years before we saw 3 of them. So it's basically the lower mass something is, the more difficult it is to find. The further away from the star it is, the more difficult it is to find.
Excellent stuff. Thank you, Simon. So next one from Mick. Thank you, Simon. Brilliant. Is Kepler still in use? Quick question.
It is. Initially, what Kepler was doing is they sent it up, and its job, it was what's often called a light bucket. So it wasn't a particularly sort of super duper amazing telescope. Putting it in space means you don't really care because you don't have to bother about the atmosphere. And its job was just to look at one small patch of sky and just keep looking at that small patch of sky. Trouble is, if you're going to do that, you need all your gyroscopes working, because you need to point really, really accurately. And then gyroscopes, being a moving part, they fail. So the gyroscopes have failed, so it's not as good at pointing in the same direction, but you can still point it and still do things with it. So it's still doing science.
Excellent. And not quite sure on this one, what proportion of the sky has SETI examined so far with no signs of intelligent life?
I'm not sure of the exact answer. I would have guessed it's looked at most of it. A lot of SETI searchers piggyback on radio telescopes, so they tend to sort of look wherever it is the radio telescope looks. There are a few dedicated searchers. When people do dedicated searches, they tend to concentrate on nearby stars that are fairly like the sun. So you look for a solar mass star, which is quite rich in metals, and you target that going, okay, if it's got a civilization, can we pick up the radio signals from it? The interesting thing about SETI is that when it was designed in the 50s, people looked at sort of plots of how much radio noise the human civilization was creating. And clearly, if you went back to 1900, it was producing none. And then we started building radio stations and TV stations and things like that. So people saw an exponential increase, and they assumed that would carry on. So they went, well, we're making a lot of radio noise, not enough for us to pick it up, but if we carry on this exponential growth of the amount of radio that's been given out, then it should be really, really obvious. What's actually happened with the Earth is the amount of radio noise we're putting out to space has gone down. And the reason is, if you think of the old RKO pictures, there's the huge sort of broadcast tower on top of the hill. That's not how we tend to do anything anymore. So a lot of our communications are done by fiber optics, or when you've got satellites, you send a signal up to the satellite and it beams it down. So we're actually producing less noise going out. And if you think, well, as time goes on, we're producing less, an alien technological civilization is quite possibly producing almost nothing. So SETI is purely looking now for deliberate attempts by an alien civilization to broadcast their existence. And it does beg the question of why you would want to do that. I think it would be a terrible idea to broadcast our existence. So there are reasons why SETI might not have found anything, which it might be telling us there's nothing there, or it might just be telling us that anything that's there is not advertising its existence.
Very good, thank you. Just a chemical chemist question, perhaps, that on your plot on the Earth's O2 content over time showed periods when it was over 25%. Would this not have caused spontaneous combustion?
Yes. the Earth with 35% oxygen would have been a really interesting place. There would have been a lot of forest fires, almost permanently. The weird thing about this is we would look at that and go, oh, that would be a really, really unpleasant time. For everything living at the time, it would just be perfectly normal. What I find interesting about that is there's lots of do we tend to think of the Earth right now as being perfect for life, but it's not. It's perfect for life that is around now because we've evolved to be optimized for the way the Earth is now. But actually the Earth's in a bit of a cold snap. The Earth's temperature at the moment is 10 degrees cooler than the average over the past 500 million years. Its oxygen content is relatively low. CO2 content is possibly the lowest it's ever been in the history of the Earth. So yeah, we just think how things are now is perfect, but yeah, to life living when it was 35%, presumably things exploding all around them was perfectly normal.
Okay, jolly good on that one. So would we be able to look for life on moons of large gas exoplanets? Obviously, it depends on the resolution of the newer technology, presumably.
Not with the next generation, even. Yeah, there's thoughts about how we might be able to find that extrasolar planets have got moons. And during a transit, you might be able to see a signal that went, aha, this thing's got a moon, but it's got to be incredibly accurate. And if you're trying to get a spectrum, it's going to be totally dominated by the light of the planet. It's difficult enough to extract what the star is doing from this if you've then got a planet that's really, really close to it. So it's a really, really interesting question. Could there be lots and lots of life on moons that we just have no idea about? Certainly not within our lifetimes. Okay.
That's a bit of a tongue-in-cheek question from Martin. Excellent presentation. What about the dinosaurs in the title?
Yes. When you're thinking about history of life on Earth and things like this, dinosaurs come up there a lot. And so I sort of went to Carboniferous, and I suddenly realized I didn't have time to
talk about dinosaurs.
Okay, and then the dinosaurs are interesting, but yes.
Okay, and I think a final one, so as far as time, is the sun's shining outside to let people sort of get outside again afterwards. So a quick one from Keith. If it was your choice, what would be the first target for the VLT?
Oh, I think probably Alpha Centauri A and B. There is reasonable evidence that there's an Earth mass planet around one of those, and that probably will be one of the very, very early targets, because I mean it's our next door sort of stellar system, triple system, and if it does have planets, that is somewhere where not within our lifetimes, but you could actually send probes to. So I think that's where I would go for it.
Wonderful. Well, thanks very much indeed again, Simon, for giving up your afternoon. At least, as you said in the preamble, that you haven't had to travel down to Nottingham.
Yeah, it wasn't like I was doing anything else.
Excellent stuff. Okay, so that's wonderful. Thank you much indeed, Simon. And we would normally, if I can give you a virtual applause, as everybody else is on mute, so I will, on their behalf, I will thank them. So what I would like to do now is to pass over to Roger Dimmock, who's the BAA Exoplanet Division Director. And so if Roger, if you would like to unmute yourself, and if I could ask Simon if you could sort of mute yourself and turn the video off as well, and that will be available for Roger then. So Roger, your screen.
You can hear me, Alan?
I can hear you loud and clear, Roger.
Right, I'll just start this up then. Share.
Thank you very much indeed.
Share. Right. So here we go. Right. That look okay? Jolly good. Good morning, afternoon, evening to all of you, wherever you might be. Professional astronomers are moving from detecting exoplanets to characterizing them. And two of the European Space Agency missions to do this are ARIEL, which stands for Atmospheric Remote Sensing Infrared Exoplanet Large Survey. Don't know who dreams these up, but never mind. And Plato, which is planetary transits and oscillations of stars. I will describe our involvement with ARIEL and Plato, covering the topics listed here: the missions, the Exoclock project, how to participate, and the mission, ground-based observations, other Earths, and the next steps as far as Plato is concerned. ARIEL is a University College London-led ESA mission, and it's scheduled to launch in 2028 and will survey the atmospheres of 1,000 exoplanets, much larger than Earth actually, super-Earth, Neptune, and Jupiter-sized bodies, which are orbiting close to their star. The BAA's Exoplanet Division has developed an excellent working relationship with this mission and providing transit observations so that ARIEL will be pointing at the right exoplanet at the right time. Some exoplanets have not been observed for many years, in fact, probably since they were discovered. So the ephemeris may now be in error. And what the mission doesn't want is for ARIEL to spend time looking at a star when the exoplanet isn't transiting it. So how do you participate in the ARIEL Exoclock project? I will talk a little about exoplanet transits. Some of these things have been covered by Simon. We didn't have rehearsal, so apologies for any duplication. The software required, how you obtain a transit light curve, and how you submit your results to the ARIEL project. Just to refresh people's memory, or those who may not have seen one of these, the planet hopefully passes in front of the star from Earth's point of view, and you get a minuscule drop in the magnitude, depending obviously on the size of the planet. The HOPS software developed by the ARIEL project is probably one of the easiest pieces of software I've used, and if I can use it, anybody can use it. Installation has not always been that easy, and we've had our problems with that, but if you follow the instructions to the letter on their website, you should get by. And they are very helpful if it comes to resolving problems for you. The ARIEL Exoclock website provides all the information you could possibly need. A list of previous observations, ephemeridays for the exoplanets, a personalized observation schedule once you've logged in and given them your information, your telescope details and so on, and the facility to upload your data to the project once you've obtained your transit light curves. Imaging exoplanet transit should be well within the grasp of anyone familiar with the basics of photometry. So if you're bored with variable star observing, you can come and join this project. Mark Salisbury's excellent article on the Exoplanet website will give you all the guidance you might need. So this is a typical exoplanet transit light curve as uploaded to the Exoclock website. It was obtained by Steve Fucher of the Hampshire Astronomical Group and University of Portsmouth students he is tutoring. What this transit curve shows is that it actually occurs slightly earlier than previously measured. Once you've obtained your transit light curve, you can go to the Exoclock website, the My Lab upload observation, and you can select the light curve you want to be uploaded, and you could submit that. Once it's been accepted, or not as the case may be, as happened to me once or twice, is that you'll receive a confirmation email, and then you can go to the Exoclock website and see your light curve in amongst all the others there. Right, moving on to Plato. That's scheduled to launch in 2028, so will appeal to some of the younger ones amongst you. And it will measure the radii, densities, ages, stellar irradiation of terrestrial-sized exoplanets, orbiting up to and within the habitable zone of sun-like stars. This is another mission we plan to get involved with by confirming Plato's detections. I think, as Simon has mentioned, there are a number of processes which might look like exoplanet transits but aren't. Star spots, stellar activity, oscillations of the star, stellar rotation, etc. And according to this slide I borrowed from Mark Kidger's presentation to the BAA last December, only about 50% of transit candidates have ever been confirmed. So this is the Plato ground-based observing program, which hopefully will get started in some way later this year. As we said earlier, the professional observatories are going to concentrate on spectroscopy, and the amateur astronomers, we can concentrate on photometry. A gentleman by the name of Gunter, not sure how to pronounce that, so I won't, is the coordinator for the amateur program. Quite a coincidence, his name coming up, because I attended a meeting in 2006, Meteors, Asteroids and Comets in Europe, MACE, at the Kuffner Observatory in Vienna. And there I am sitting right next to Gunter. He's the guy on the left. I'm right behind him. Quite some coincidence that, so hopefully we'll meet again when we get out of the lockdown. And you can see Richard Miles at the back there, back right. Now, other the facts according to Mark Kidger, very few and far between, as you will see. But there are many, many exoplanets out there, 4,000 as was mentioned earlier, so I'm sure there will be a few. Other slightly less pessimistic estimates, there's 21 possible habitable exoplanets out of a total of over 4,000. And I've known Mark for many years now, and so we're looking forward to establishing a good working relationship with the Plato team. Hopefully towards the end of this year, we'll get something off the ground when we all get back to normal. NASA's test satellite was mentioned earlier, and the ESA Plato launch, which is 2028, they're both going to provide targets for the James Webb Space Telescope, which may or may not launch in 2021. And as Simon mentioned, the ELT. So with those telescopes up there, we'll really get some good ideas about the character of the exoplanets themselves. But all the aerial information can be found on the BAA Exoplanets website. Plato documentation will follow later, as I mentioned, when we got things together at the end of the year. But if you're at all interested in exoplanets, go to this website. I'm sure you'll find something that will have interest you. So that's all, folks. Thank you very much for listening.
Thanks very much indeed for that, Roger. So that draws the webinar to a close for today. Thanks again to Simon, to Roger as well. So Roger, if you'd like to close your screen down, that's good. As far as the webinar, next webinar is coming up, we've got a Twilight Tour of the Moon webinar, which is being done next Wednesday. That's the 29th of April at 7 o'clock, the usual time for the webinars. David Arditi will be doing that, and hopefully the fair weather will be continuing. So so without further ado, the recording of this will be available on YouTube as well, if you'd like to catch up any aspect of it.
Just one point before you go, Alan, if
yes.
I could. I noticed I lost nine participants during my talk. Do we know who they are?
I'm not sure. It was an excellent talk, though, Roger. Don't take it to heart. But no, I'm not quite sure whether we do. We'll check with Dominic afterwards. But we'd like to draw it to a close now. But I hope that everybody enjoyed it. I know we couldn't get to Nottingham, but I hope that this was a bit of a replacement. And I hope that as BAA members that you're enjoying the sort of technology that we're bringing to you in the way of webinars on a regular basis. And I hope that we continue to enjoy them, and that we can look forward, hopefully, to the next meeting, which I think is, at the moment, is scheduled for Leeds in September. But who knows whether things will have cleared up by then. So that's great. Thanks so much indeed again. So now we'll be closing the meeting down. Thanks so much indeed. Bye-bye. Dominic.
Hello.
Hi there.